Hello, and welcome back to the Cracking FAANG YouTube channel. Today we're going to be solving Leetcode problem 236, lowest common ancestor of a binary tree. Let's read the question. Given a binary tree, find the lowest common ancestor, LCA, of two nodes in the tree. According to the definition of an LCA on Wikipedia, the lowest common ancestor is defined between two nodes P and Q as the lowest node in T that has both P and Q as descendants, where we allow a node to be a descendant of itself. So, let's look at an example. If we're given that P equals 5 and Q equals 1, so this node here and this node here, then we would want to return 3. Why is that? Because obviously this is the first node where they converge when going up the tree. So this is the lowest common ancestor in the tree. Okay, but what about the example where we have P equals 5 and Q equals 4? So this is here and here. Here we want to return 5. Because if we think about it, if we go up from 4, we're actually going to reach the 5. And since 5 is allowed to be an LCA of itself, right, based on the definition from the problem, this is actually the lowest common ancestor. So that's why we return 5 in that case. But what about this case where P equals 2 and Q equals 7? Well, again, because we allow a node to be an LCA of itself, the 7 and the 2 meet here at the 2. So that's why we're going to return 2. So this problem is relatively simple in that there's only 3 cases that can occur. And we've actually just gone over them with these examples. In the first case, the two nodes will be on opposite sides of the tree. And what we want to do is we want to find the first node where they converge, where they would meet. So the first node where going to its left and its right, we would be able to access both the nodes. So that's the case when P equals 5 and Q equals 1. The second case is where P is, Q is a descendant of P, which means that P is actually our LCA here. And then the other case is going to be where P is actually a descendant of Q, and then Q is going to be the LCA. So that's going to be this case 3. So essentially, those are our 3 cases, and solving this problem is quite simple. What we want to do is we want to do a depth first search through our tree, and we're going to start at the root, and we're going to check, okay, can we reach the P or Q from this node, right? And what we're going to do is check whether or not the current node equals to P or Q. If it does, then we can return that node to the parent. So let's do this example. So we're at P, Q, and we start at the 3. Does 3 equal to either P or Q? No. So that means that we go into the left subtree and we go to the right subtree. So we'll go to the left first, and we're at this 5. Does 5 equal to P or Q? It does. So that means that we can return 5 to this node here. And then we stop there because we found a node. So either Q will be found on the other side of the tree, or it's a descendant of 5, which is fine because we would just return 5. So we don't even have to explore the rest of the tree because we know that either it's going to be down here or it's going to be on the other side of the tree. Since P and Q are guaranteed to exist in the tree, we know this is true. So if 5 is actually the LCA, then we can just return it. That's fine. If it's not, then 3 will receive a non-null node from both sides, in which case we know that it is the LCA. So we said that we're going to cut the processing here because we've already found P. Then we go into the right subtree and we say, okay, does this node 1 equal to either P or Q? Which it does because it's Q. So we would return 1 here. And when we receive a non-null node from both the left and the right, we know that we found an LCA. So we can simply, pass up our current node. So we would return 3 here in this example. But let's look at this example here where, Q is actually in the subtree of 5. What's going to happen? So again, we start here at this 3, and we're going to say, okay, does this equal to either P or Q, right? Is it 5 or 4? It's not, so we need to go into both the left and the right subtrees. So we're going to go into the left subtree, and we're now at this 5. And we're going to say, okay, does the 5 equal to 5 or 4? It does. So that means that we can return 5 here. And that means we can stop searching for the rest of the tree, because remember, either 4, the Q that we're looking for, is going to be in this subtree here, or it's going to be on the other side. So now we can go into the right subtree, and we end up at this 1 here. And does 1 equal to, does 1 equal to 4? It doesn't. So we're going to try to explore the left subtree. So we go into the left, and we go to the 0. And does it equal to 5 or 4? It doesn't. So we try to go into its left subtree and its right subtree, but those don't exist. So we just simply bounce back to the 0. At this point, we haven't found any, we haven't found P or Q in this node or its children. So we would simply return none here. And now we try the right subtree of 1. Again, does 8 equal to either 5 or 4? It does not. So that means that we need to go into its children. So we try the left subtree, obviously that is null. We go into the right subtree, that's null. So that means that we haven't found 5 or 4 in the left or right subtree, nor does this node equal to 5 or 4. So that means from here, we return none. And that means that from 1, we haven't found it in its left subtree or its right subtree, and obviously 1 doesn't equal to 5 or 4. So from here, we return none. Now we've fully explored 3's left subtree and right subtree, which means that we check, okay, did we receive a non-null node from both left and right? We didn't, but we did receive a non-null from the left, which means that the LCA must be this node here. So we're simply going to return up the tree this 5. And if we had more nodes, we would keep going, and either we would get to a point where a current node receives a non-null from its left and its right, in which case that is the LCA, or we'll just pass up the tree, and it has to be the case that the non-null node we kept returning is the LCA, because that means that the node, the other node was in the subtree of the other node, of the node that we did find. So if that makes sense, right? The reason we don't have to explore everything is because either it's 5 or it's in the other side of the tree, and that's essentially the algorithm we want to use for this. So hopefully it's not too confusing. Once we go into the code editor, it's just a few lines of code to solve this problem, so hopefully it clarifies things a bit. If not, kind of go back and let's walk through all 3 of the examples again, and hopefully it makes a bit more sense. So I'll see you back in the code editor, and we'll write out the code for this. We're in the code editor. Let's write the code. The first thing that we want to do is actually check whether or not our tree was given to us, because if we don't have a root, then there's nothing for us to search for P and Q. We should just return none. So if not root, we can simply return none. I think actually for this problem, we are guaranteed to have those nodes, but it doesn't hurt to do this. A lot of the times you will get tree questions where the root can be null, so just working with your interviewer, identifying that base case, just shows that you're thinking about the edge cases and you know how to handle it. So even though we don't technically need it for this problem, I guess it's just good habit to have for any sort of tree-based question. Okay, moving on. What we want to do is we want to say, okay, if the root equals to either P or the root equals to Q, then remember, then we can return that node to the next level. So we can simply say return root. And what we're going to do is, if we haven't returned at this point, then we need to go into, the trees left and right subtrees. So we're going to call our lowest common ancestor function recursively. So we're going to say left equals to self.lowest common ancestor, and we're going to call into the left subtree, right? Root.left, and we're going to pass in PQ. And now again, we're searching for P and Q in the left subtree, and we're going to do the same thing for the right subtree. So we're going to say self.lowest common ancestor, and we're going to pass root.right, PQ. And now what we need to do is we have left and right. And remember, if left and right are both non-null, then that means that the current node that we're at, this root, has to be the lowest common ancestor if both are non-null, right? Like for example, we're looking for 5 and 1 here. So 5 would return non-null and 1 would return non-null, right? It would return 5 and 1 respectively. That means that 3 is the lowest common ancestor. when we receive only one non-null, then we want to return just the non-null one to the next level in hopes that we will find a point where both sides return non-null, or we will just keep going forward with the one that was, defined, and that will actually be the LCA in the case that, the other node that we're searching for is actually in the child of the node that we're returning. So either they're going to be on different sides of the tree, in which case they're going to converge at a point. So one node will receive non-null from both its left and its right, or, one node is a child of the other one. So that being said, remember, we're going to say if left and right. So if they're both defined non-null, then what we want to do is just return the node that we're at. And otherwise, we just want to return the one that's defined. So we're going to say L or R. So the one that isn't null, we're going to return to the next level. And if they're both null, then obviously we'll just return none, and we'll keep doing that recursively. So let's submit this and verify that it works. And it does. So what is the runtime complexity of this algorithm? Well, the runtime complexity is going to be based on the size of the tree. And it's going to be a big O of n solution, because in the worst case, we would need to go all the way through the tree. So if you think of a tree that's like an inverted V, we would have to go all the way down to the left to find P, and then all the way down on the other side to find Q, and then we have to recurse all the way up back to the root of the tree to figure out what the LCA is. So in that worst case, it would be big O of n. And what about the space complexity? Well, technically it's, big O of 1, because we're not defining any extra data structures here. We're not even allocating any extra space. But we are doing a recursive solution, so we do have to account for the fact that if our interviewer wants us to count the recursive stack frames, then we have to account for that. So we're going to say big O of 1 if not counting recursive stack frames. Otherwise, it's going to be, big O of n to account for the recursion. So that's going to be your time and space complexity. And this is going to be how you solve the problem. Again, it's super simple. It's just a few lines of code, and it's, relatively straightforward. Especially once you've seen it, you can kind of work your way through why it works. It's really not that bad of a question. So that being said, if you enjoyed this video, please leave a like, comment, subscribe. If there's any other videos you'd like me to make, please let me know in the comment section below. I'd be happy to help you guys out. You just have to tell me what you want to see, and I will get that out for you. Otherwise, have a nice day and happy coding. Bye.